So first I'd like to thank Alex and Frédéric for organizing this conference, or this colloquium. It still feels a little surreal to be giving a talk to people in flesh instead of in pixels. So I'm going to be talking about some work I did with Elam Kashefi and Damien Markham, where we really tried to integrate cryptography into quantum metrology. And I've partitioned this talk into 3 different sections. I'm first going to go over some key ideas from quantum metrology, as it's a little different from the other themes today. And then I'll spend most of my time trying to motivate the reason on why you might want to incorporate cryptography into metrology and develop the framework. And at the end, I'll give an example of a this enhanced, or this quantum metrology enhanced with crypto scenario, and an example of a protocol that we developed. So for those who don't know, metrology is just the science of measurement, and so quantum metrology is just in a quantum setting. So now we're using a quantum probe to measure a physical quantity, and for example, in a classical example, you might have these old-timey thermometers with mercury, and the mercury will expand and contract, and that acts as a probe for temperature. And we really want to take advantage of quantum effects to achieve enhanced measurement precision. And as a theoretician, I like to think of quantum metrology as a kind of 4-step process. Very simple. We're going to prepare some sort of resource state psi, and then through some sort of physical interaction, we're going to encode an unknown parameter theta into our quantum state, and then we'll measure this quantum state, and if we chose some sort of correct measurement, the measurement results should depend on theta, and if we do this enough times, then we can reverse engineer the results to obtain an estimate of this unknown parameter. And I forgot to say, but feel free to stop me at any time, either for a question or for clarification. And just some key nomenclature from quantum metrology and statistics that I'll reference a few times later on. Fisher information is just this quantifier that describes the amount of extractable information we can obtain about an unknown parameter through some sort of scheme. So in the quantum realm, our schemes are our measurements, so the Fisher information will depend on the quantum state and our measurement basis. And then quantum Fisher information is just this maximized over all possible measurement schemes. And in classical statistics, there's a relationship between the variance of some parameter and the inverse of the Fisher information. And so the quantum Cramer-Rao bound, this extended with the quantum Fisher information. And when we saturate this bound, it's called reaching the Heisenberg limit. And the reason for this name is because if you do phase estimation with a pure state, where your unitary is generated through some sort of Hamiltonian H, and you rewrite the equation, you get something that looks, you get something that looks like the Heisenberg uncertainty principle. So how do we actually measure? These inequalities are nice, but what is the actual variance if we do some sort of measurement scheme? So in practice, some sort of observable O is measured, and then we actually estimate the value of the expectation value of O, and we then invert that equation to then obtain some sort of estimate theta hat. And if you remember, or if you took physics or engineering, then the error propagation formula is something like this, where nu would be the number of quantum states or measurements that were done. So just for an example of comparing classical to quantum, I have this classical state where there's no entanglement, and this maximally entangled GHZ state. And in both cases, we're going to encode some sort of phase. Maybe this is through a magnetic field. And we'll use the measurements to obtain an estimate of theta hat. And if we measure in any sort of basis that's orthogonal to z, so x, y, or any combination, in the classical setting, we get this 1 over n scaling, which is just the central limit theorem. And then in the quantum scaling, or in the quantum scenario, we actually get this 1 over n squared. And this is known as the Heisenberg limit, as I mentioned. And it's really important, you can think of it as increased precision, but people are more concerned with actually saving resources, especially in biology and medicine, where probing a sample can be damaging. So if we can do, for example, like when you're doing imaging with X-rays, it's harmful to the body. So if we can get the same precision with some sort of quantum X-ray or squeeze light, then this would be nothing but beneficial. And as of right now, you might be wondering, why do we need to incorporate quantum cryptography? Like, it really seems like something that you do in a lab. You prepare a quantum state, you have it interact with something, and then you do measurements yourself. But I'll try and motivate some scenarios where actually we really need this cryptographic notion of security. And the first example first set of examples I want to talk about is when you're doing some sort of distributed setting. So maybe you can imagine in Paris you have different probes that measure maybe temperature or pressure, and we want to measure the gradient of such a function. Or maybe we have just this network setting like the Quantum Internet Alliance proposes, where we have different nodes measuring, and you're doing this multi-parameter metrology. Really, any spatially distributed scheme, though, will have to distribute resources through a quantum channel, and generally, quantum channels are seen as the weak point. We generally trust classical channels, and quantum channels can be altered, or it can be really hijacked. So we would need to take proper precautions. Otherwise, the estimate at the end is really useless if we don't know what's going on. So on the right here is, I think, like the most spatially distributed that I can think of, as it's around the entire world. And it describes, it's from Komar et al. From 2014. It's called a network of quantum clocks. And so you have these different satellites, and it's really a giant GHZ state, and then each node is a GHZ state. And the goal is to really synchronize these clock synchronization. So you have these ticking qubits, and maybe they're dephased, and so we want to measure the phase between them. And they exchange everything through the central node, through quantum channels. And I actually do really like this paper because it was the first, at least as far as I'm concerned, what I could find, it's the first notion of security. Like, they do propose some sort of notion of security, although it's a little, it doesn't exactly hit the mark. It wasn't the main point of the paper, but it's interesting nonetheless. So in any of these spatially distributed schemes where exchanges are used through a quantum channel, we should think about incorporating quantum cryptography. Another task, or another scenario where it might be practical, is for when tasks are delegated. So again, in this kind of proposed Quantum Internet Alliance throughout Europe, we have these different nodes that have access to different quantum technologies. So maybe I do want to do some sort of quantum metrology experiment, but I'm not able to prepare my own GHZ states, or maybe I can't do my own measurements. So I have to ask some sort of third party to do this for me, and if I don't necessarily trust them, I have to incorporate either verification or some sort of blind quantum computing protocol. But regardless, we have to include crypto once again. And the last kind of very generic setting, and these kind of go in the last two, is just to have some sort of notion of security or privacy. And both of these papers come from groups in Japan. So the one on the left, it's a quantum metrology scheme where you have this network setting again, and different nodes in the network have some sort of encoded parameter and some have none, and they want to create a protocol to hide which nodes have an encoded parameter and which ones do not. So some sort of privacy. And the one on the right is, I guess it fits in this delegated quantum metrology setting that I've described. They don't have access to measurement technology, and so they use some sort of blind quantum computing protocol where they have to send all of their measurement results to a server, but they want to hide the information from the server. So in all of these cases, we have to include some notion of security, or sorry, cryptography. And it has been done a few times, but what has been missing from these types of studies is how it affects the quantum metrology component. So something that's sorely lacking is an answer to this question of just, is this error propagation still valid? And the answer is obviously not. Because as soon as we're including this cryptographic notion of a potential malicious adversary, we're inherently assuming that we're making the assumption of additional uncertainty into our resource, whether that's our resource prior to metrology or our uncertainty in our measurement results. So somehow we have to change this in a cryptographic setting. And so what we try to do is take these common cryptographic quantifiers, such as privacy and soundness, which I'll define later on, and we would try to incorporate them into some traditional metrology quantifiers, like the estimate value and the precision or the variance. And just in the paper, we call this integrity. So to do this, we consider two different scenarios. One is what you would expect in the ideal case, and the second, what you might expect in a potentially malicious case. So ideally, we have a bunch of copies, so new copies, of some sort of encoded state rho theta, and in the malicious case, we have no idea what we have. It might not be encoded with theta at all. There might be massive entanglement. We don't really know. The only thing we do want is that on average, it's close to our quantum state, or it's close to the ideal state. So here I define this superscript bracket j to be, if rho theta is n qubits, then the superscript bracket j is the jth block of n qubits. And d is the trace distance. So this is saying on average, what we're using is close enough, and we demand that epsilon squared is small. So if this is the case, then probably the smartest thing to do is to still pretend like we had the ideal resource and continue forward. And in doing so, we find that the estimate itself is biased with a little bit of uncertainty that scales like epsilon, and little o is the maximum eigenvalue of your observable O. And the variance, so this additional error then propagates to the variance, and we now have additional uncertainty that scales like epsilon squared. And so back to this canonical GHZ example, where we want to recover the Heisenberg limit, we find that when we plug everything in, we get something that the larger term is this 4 epsilon squared over n squared. So to recover the Heisenberg limit, we would need epsilon to scale like 1 over the square root of the total number of resources, which makes a lot of sense because in the ideal case, we have in theory, I know it doesn't work this way in practice, but in theory, if you have an infinite number of resources, then you can obtain infinite precision. And so if we want to do this, if we want this infinite precision as nu goes up, we need the additional uncertainty in our resource to similarly go to 0, or at a similar rate. So the two cryptographic quantifiers that I mentioned earlier were privacy and soundness. So privacy is extremely simple. It's not necessarily a quantifier actually, but more of a concept, and we don't want any information to be extractable. So in that satellite example, if we send the phases going back through the quantum channel, we don't want some sort of third party to be able to access it and then extract the dephasing information themselves. And then we have this notion of soundness, which is a little confusing, and if you are familiar with crypto, you might be familiar with a different definition. But I've written, I think, the simplest mathematical statement I could construct. But it measures the ability to detect alterations made by a malicious adversary. So generally in a cryptographic protocol, you have two outputs, like the output you're going to use, row out, and then you also have this binary accept or reject clause that you make by measuring ancillary qubits. So this is really saying that if I accept that there were no alterations, this doesn't mean that there were none, it's just I'm accepting that there were none, then the quantum state that I get is pretty close to the ideal state. So we want this whole quantity to be small. And if it's not clear now, I think it'll be clear later on. And this isn't actually quite good enough to work with yet. We do have to make another assumption that we can at least bound this acceptance probability. And you can do that either by changing the accessibility of the channel or maybe limiting the types of attacks an adversary could do. And by extracting this and by absorbing this expectation value into the quantum state. So now here this row out is really the expected output state. Then we can bound the fidelity. And there's some fidelity and trace distance relationships where we can now set this value of epsilon to be the square root of delta over alpha. So now I have a link between this cryptographic notion of soundness, and I'm able to link it to our variance and our bias through some sort of metrology scheme. So with this in mind, I want to explore a simple scenario where we are using this quantum channel in our experiment. Maybe it's a network setting or maybe it's a delegated setting, but we have to use some sort of untrusted quantum channel. So we can think of, we have three parties, and two of them are trusted, Alice and Bob, and we have some sort of malicious adversary, Eve. And for this, we can either we can say that maybe Alice prepares the quantum state, and then Bob encodes and then measures it, or Alice prepares and encodes, and then Bob measures it. It doesn't really matter which one, we get these same results. So for all intents and purposes, we go ahead with the prepare and encode. That way there is information about the unknown parameter accessible to Eve without the use of a cryptographic protocol. Yes?
What do you encode? Like on Alice encode?
Oh, so by encode I mean like encode the unknown parameter. So here, prepare, I have my resource psi, and then when I encode it, I have psi theta. So I'm not doing any sort of encryption yet, but I will. So to translate this very base schematic into crypto schematic, yes?
So you want to measure something, and in both cases, this something is either with Alice or Bob, right? Or like, what is like? You want to measure
Yes.
What is physically this parameter? Is on Alice's side or Bob's side?
Oh, that's what I'm saying. It doesn't, for this simple protocol or for this scenario, it doesn't matter if it's Bob who has access to it or if it's Alice. It's just one of the two. Like our protocol will be the same for either scenario. Yeah, but so for all intents and purposes, we go with scenario 2. But it would be the same protocol regardless. So to actually use the quantum channel, we can't just send in our quantum state bare boned. We have to do something to it. So Alice is going to create this input state, which I've labeled row in, and then Alice will perform some sort of encryption. We assume that Eve has total power and can do any sort of CPTP map, capital gamma, and then upon receipt, Bob will decrypt this and he'll measure the flag qubits. So flag qubits are additional qubits in the quantum state that aren't used for metrology, but purely this accept-reject hypothesis. So row in will be a combination of blue circles and T purple triangles, and the blue circles are the ones for quantum metrology, and the purple triangles are just prepared in the computational state 0, and it's randomly permuted. So they're randomly inserted within this total number of qubits, which is M. And then I wrote protocols with bracket S because it's 2 protocols, but it's really one protocol disguised as 2 with different hardware assumptions. So for the trap code, I have that the encryption and decryption are single qubit Cliffords, and in the Clifford code, it's any arbitrary Clifford operation. And so obviously, we're going to see that the Clifford code scales much better because it generally generates entanglement between the flag and the metrology qubits. And it's really easy to show that we do achieve privacy since Eve has no information about our encoding. The expected state for Eve is the maximally mixed state. And then for soundness, we achieve this linear-like scaling, or this 1/t-like scaling for the trap code, so no entanglement is generated. And we get this exponential scaling, or 1/2 to the t scaling for the Clifford code. And again, this is purely because of the generated entanglement. And actually, we originally had a more complicated protocol in our paper where Alice sends something in just to get it encoded by Bob. So this is what I meant by encoded. He encodes some sort of parameter theta and then is sent back to Alice. But one of the referees said that the scenario was maybe a little too convoluted and we should consider just one pass through the quantum channel. And we use this more convoluted example as this was actually what was originally done by Huang, Machiavello, and Makone in their version of cryptographic quantum metrology, which kind of inspired our paper as they looked at this scenario, but they never made the connection between the cryptographic protocol and the effect on how it affects the variance and precision. And also they use a different protocol, more like BB84-esque, but we showed in our paper that there's a protocol that Eve could do that would be undetectable by Alice and Bob, and then Eve could also gain information about the unknown parameter. So just to summarize the 2 protocols, or if we recall, we need this epsilon parameter to be like 1/the square root of the total number of resources. So the trap code, we recover the Heisenberg limit with really this is each run. So it would be like 3, the total number of extra resources will scale like nu squared. So a quadratic increase. And for the Clifford code, we would need nu times log nu, so a log linear increase if total number of resources. And to summarize kind of everything, this is really, I think, the first formalization of crypto and quantum metrology. Like, it has been done in the past, but it was really lacking that how does this cryptographic setting actually affect the variance of with respect to quantum metrology. And we did this by linking your typical quantifiers, namely soundness, to quantum metrology. And just for an application base, we constructed both a secure and private protocol over an unsecured quantum channel. And moving forward, I would really like to, as this was a very general setting, I'd really like to tailor protocols to specific attacks or implementations. So, for example, we could consider some sort of photonic implementation, and maybe the malicious party is loss or dark counts, or maybe we're only looking at Pauli attacks and we can get much better notions of security. And then I would also like to extend this to other frameworks, namely multi-parameter quantum metrology. So here I've only talked about a single scalar, but in general we can consider theta to be a vector, and then instead of having this variance relationship between the Fisher information and quantum Fisher information, you have the covariance matrix and the Fisher information matrix, et cetera, et cetera. And I think this scales, or this generalizes in a pretty straightforward method, but what I don't think would be as trivial is going from a DV space to a continuous variable Hilbert space. I think some things would actually have to change. The other talk ended a bit early, and then so did mine, so I'd like to thank you for your attention.